we're gonna decode chess. But let's be clear, this isn't really about the game. It's about pushing up against the absolute limits of what's even possible to compute. Welcome to the Deep Notes Lab. You are entering a space dedicated to signal, not noise. Here, we decode the black boxes of technology, data, and system architecture. And today, we're using a very specific lens to do it. So let's start with a puzzle, really. It's a question that's fundamental to system design. How can something completely closed off, with a fixed set of rules, create a level of complexity that's, well, practically infinite? Okay. To even begin to get our heads around that complexity, we have to map out the system itself. Let's start there. The system, a finite universe. You know, when we look at a chessboard, what we're really seeing is a perfect case study. It's a completely closed system. You've got your 8x8 grid, 2 players, 16 pieces on each side, and a set of rules that are totally defined. There are no unknowns here, in theory. And this simple, finite system, it became the backdrop for a huge moment in the history of computation. We're talking May 11th, 1997. World champion Garry Kasparov, arguably the greatest human chess mind ever, is beaten by IBM's Deep Blue. And just like that, the paradigm shifted. For the first time, a machine was the best chess player on the planet. But here's the thing, Deep Blue's win wasn't just about knowing the rules better. It was about its ability to handle a problem of absolutely staggering scale. And that brings us right to the heart of the issue, the problem of exponential scale. Look, the game starts out simply enough. After each player makes just one move, you're looking at a few dozen possible board states. That's manageable. A person, a basic computer, they can handle that, no problem. But that simplicity just vanishes. The complexity doesn't add up, it multiplies. It just explodes. By the time you're 10 moves deep, the number of possible games skyrockets to almost 70 trillion. And right there, that's when you start to feel the true weight of this problem. And this is where the scale just becomes mind-bending. The total number of possible chess games, what we call the Shannon number, is 10 to the power of 123. To give you some context, the best estimate for the number of atoms in the entire known universe is around 10 to the power of 80. So trying to brute force a solution, it's not just a bad idea, it's physically, fundamentally impossible. Okay, so if brute force is completely off the table, how in the world do you attack a problem like this? Well, as with any massive system, you start architecting a solution. You build logic. From an architect's point of view, solving a system like this really just means mapping all of its possible states to the best possible outcomes. You're building the perfect roadmap. But as you know, there's always more than one way to draw a map. We really have two main approaches here. First, there's the strong solution. Think of this as the holy grail, a perfect, absolute map of every single position leading to the guaranteed best move. It's flawless. Then you have the weak solution, which is much more practical. It's about finding one single optimized path to victory, and it does that by just ignoring all the obviously terrible moves. It's that classic trade-off every single one of us has to make. Do you build the perfect, exhaustive system or the pragmatic one that actually gets the job done? And this is exactly where theory collides with the cold, hard limits of reality. We've actually built strong solutions for chess endgames, but for just a 7-piece endgame, that takes 140 terabytes of storage. Scale that up to an 8-piece endgame, and you're looking at 5 petabytes. And a weak solution for the whole game, even if we optimize everything, our best supercomputers would need over 1 trillion years. 1 trillion! The physical constraints, the storage, the time, they're the real walls we're hitting. So why do we care? Why does analyzing this old board game have such massive implications today? This is the real takeaway. Let's talk about the application, network search. Think about it like this. Every single move in chess isn't just a move. It's a node in a giant sprawling web of connections. And an entire game, that's just one possible path you can trace through that network. And once you see it that way, you see it everywhere. This exact model, finding the best path through a network of nodes, it's the logical core of so much of our digital world. We're talking about mapping user connections on social media, optimizing supply chains and traffic routes and logistics, and even training AI to navigate incredibly complex and intuitive environments. It's all the same fundamental network search problem. Which brings us to the key principle, the one big thing we can pull from all of this. Real efficiency isn't about calculating more. It's about calculating smarter. It's about that critical shift from just brute forcing the data to intelligently finding the signal within all that noise. This is your roadmap. Trust the logic, build